Good afternoon, everybody. Welcome to the transport session relating to metamaterials. My name's Steve Morris. I actually work for the KTN, and my expertise is not transport. You might be interested to hear. So let's kick things off on the basis that I know what I'm talking about, and I'd just like to kick off with my presentation. Okay, so what we're talking about here is that the conference is obviously about aligning metamaterials technologies to commercial opportunity. Rather than talking about the technologies and the advances in technologies, I want to talk about how they're being applied. As I said, this is about transport. I guess we might be talking more about automotive and mentioning rail at this point in time. So we're not covering things like the marine side. And indeed, the aerospace and sort of aviation part of transport was covered this morning in an earlier session. So, so what's a metamaterial? Always an interesting one. This is a definition that's been used before in some of the events that we've run on metamaterials. And it's, well, this you can read it for yourself. They describe it as a composite material in which, you know, constituents are designed, and you can read that. It's all very nice and self-explanatory. I often decide to describe a metamaterial as a material that is designed to deliver specific function or functionality in a device or system. In the past, that's how I describe it. In the past, we've talked about materials that are not found in nature. I always dispute that one, and in fact, I would give you a couple of examples where metamaterials are used or found in nature, and that's interesting enough in insects. Moths' wings have a design that allows that is effectively down to acoustic metamaterials, which allow them to fly silently. And the other option, of course, is butterfly wings, which use visual light to color their wings effectively. So that's using metamaterials too. So there we are. They are found in nature. I'm happy to talk to anybody about the definition, but that's how I see it, and that's essentially how it's seen in government circles. So what are we talking about? Well, there are a number of different types of metamaterials, as I've already alluded to. Acoustics, we've just run an acoustics session this morning, and in fact there's another one at the moment related to the built environment and construction. So we're talking about you know, controlling sound, and indeed it's often linked to controlling thermal properties too. So you can add some of these materials to traditional sound barriers in rail and road systems, for instance, to improve the efficiency of the acoustics, although that's quite a broadband type thing. But yeah, it can obviously improve the acoustics, and you can keep the thermals under control too. There are examples of, you know, controlling industrial machinery sound, but still allowing them to cool, that sort of thing. Then there's the electromagnetic area, which is what we might be talking about here when we talk about LIDAR. And we've got mechanical ones, which we aren't actually covering at the moment, but are often found in things like the healthcare sector for things like orthopedic implants, where the nature of mechanical metamaterials means that they that allows a better fit for things like hip replacements. And then, as I say, I mentioned thermal already. That's about control of obviously of heat. So, as I said, role of metamaterial. This is just a few examples, and then lots of pretty pictures to help you understand what we're talking about. And a lot of the technologies that are being developed in universities relate to all these sorts of things, but not all of them are at this present time seen in a commercial light. But there's certainly lots of activity in all those hot topics that you might expect. That we're currently struggling with, which is things like green energy. So energy harvesting is a very key area. You know, whether we're talking about picking up solar energy and improving solar cell technology, or whether we're talking about energy harvesting from things like a moving train, for instance. The noise control I've mentioned. We're talking about improving imaging, so flat, more efficient lenses. We're talking about metasurfaces, so wireless energy transfer, that sort of thing. So quite a wide range of potential areas that they can be used in. And some, as I say, some are well-known commercial ones, like antenna, like LIDAR for connected vehicles. And some are still on that cusp between being in the laboratory and going through scale up into commercial activity. And it's quite a wide-ranging area for metamaterials, as I've said. So if you're looking at if you live in London, for instance, and you're looking at your window, you might see some of these things, the roads and that. And we're talking about all sorts of things. So controlling noise in vehicles, controlling pollution. We're talking about controlling heat and light coming into houses through windows. We're talking about focusing Wi-Fi signals through windows, so you get better Wi-Fi connectivity within your house, and a whole range of types of metamaterials. So now on to the transport bit, which is a little bit more interesting for the session, but also it's an area which me as an expert as an expert in materials, but not necessarily in transport, that I was trying to find out some things about what the current challenges are in the transport sector and how these might relate to shall we say the use or the added value that metamaterials can bring, and these are some of the things that I found, and I guess that we're talking about, as I said, connected vehicles and even even sort of the future of vehicles in general. So not just connected vehicles, but vehicle safety and vehicle power as well. So we know everybody's going electric, or if it's large transports like lorries or buses, that we might be going towards things like hydrogen. But the metamaterials are being looked at in a lot of these areas, and as the areas become more apparently sort of exciting to the public and to the government, of course the opportunities will increase, and these include lightweighting. And I know that we've got a speaker coming on after me who is going to talk to us about some of the potential areas for composites that relate to a lot of the stuff about data and data transmission. So that's all very relevant too. Obviously I'll leave Jasmin to talk about that in a minute. So that's really a sort of general sort of overview of where we were thinking things were. So I just want to go on and talk a bit about vehicles, shall we say. So here, these are some of the options that are, shall we say, have been looked at, and quite a lot of this stuff has been looked at by some of the big manufacturers like Toyota and BMW, and in fact, whilst they're reported as talking or looking into increased safety in cars, including things like active heads-up displays to warn of forthcoming sort of objects and risks and the like, and about sort of connecting to other vehicles on the road. As we get more and more vehicles, it becomes more apparent there's more chance for accidents, and the opportunity to for the vehicle itself to keep an eye on where you are and what's happening, to improve your views of the roads and what's coming up, and indeed to transmit data to collection points for various things. I mean, I think the traditional sort of things like tire pressure monitoring systems are quite well known now. And I know the cars that we have warn you when the tire pressures have fallen. So that's quite sort of well established stuff. But I'm thinking more about the avoidance of collisions and the like, and improving people's perception of what's coming up. So the car helping you to understand what the potential risks are that are coming up on the road. And extending this a bit, these are some of the, as I say, some of the things that are involved in that space. It's a slightly different sort of way of looking at things, but we're still looking at the same sort of stuff. And these are the sort of frequencies that are required for some of the safety features. And we're all seeing things like LEDs on our cars now, which improve our view to other road users, shall we say. And I think increasingly important will be those connections and those understandings of what's around the car and how the car can help you understand what risks are coming up in the future. And I suppose if you take it on to the next stage, we're talking about things like, well, can we take this and use metamaterials, in terms of wireless charging? So if you've got an electric vehicle traveling along the road now, I guess this is not going to happen tomorrow. But if you have a lot of electric vehicles, can you use the road surfaces to charge the cars as they travel? And obviously the metamaterials there would be used to sort of focus the beam so that the car can pick up the energy. I mentioned to you that one of our KTM people is an expert in the rail side. I'm going to apologise to Daisy straight away about the next slide, because I'm not sure I fully understand it, but it's about energy harvesting, and I felt it was worth mentioning that we're talking about slightly more than the automotive opportunities. And this one's particularly focused on using the energy harvesting, I guess, to help address the acoustics and indeed the energy requirements of trains. So these are some diagrammatic sort of views of how it works and how metamaterials can help reduce that sort of acoustic noise and also harvest energy at the same time that could be used to power systems. So, and I'm now going to spare you all me talking any more about transport, because I'm sure you've all realised now that I know very little about transport, and now my understanding is that we were to have a speaker from the USA who was going to talk to us about LIDAR systems for connected vehicles, but unfortunately it seems that he's not available. Ooh, he's not available. So we're wondering whether his alarm has not gone up this morning, because he's on the west coast of America. So he's quite early in the morning for him. So I'm guessing that I need to pass on to my second speaker, Jasmin. Jasmin Stein it works for TWI and is a section manager in advanced composites and adhesives. And Jasmin is going to talk to us about lightweighting, really. So use of composites in vehicles, where we can perhaps look at the composite construction and try and change the way we could transmit data and not use wires. So Jasmin, I would like to pass over to you. If you'd like to share your screen, I'll stop talking.
Thank you very much, Steve. I hope you can see my screen.
Yep, perfect.
Okay. Good morning, good afternoon, and good evening to those who are joining from different parts of the world. As Steve mentioned, I am Jasmin Stein. I'm working for TWI.
Your sound's not so good, Jasmin. Have you?
Can you hear me now?
Yes, that's much better. Yeah, okay. It was just going in and out a little.
Okay, I'll try to speak up. I work for TWI in the advanced composites and adhesive section. I manage the team, and my background itself is composites. I have been working in the field for about 15 years now, and now I have actually turned into a bit different area in composites. And actually what I'm going to talk about would be, yeah, it's a composite, but not as you know it. So I'll give you a bit of a background first. And I'm not necessarily going to reference to metamaterials constantly, but you will see why this talk has come under this session. When it comes to cars, you will know not only cars, even in aircraft sector, nowadays it becoming more and more complex and sophisticated to make it a more enjoyable experience for the travelers. But this means the internal systems getting more complex, and that means you also have more and more cables in the system. In a car, you may use extra cables or wiring for sensor data, or to send camera signals or data, for actuations and control systems, and for certain level of communications as well. This means you have different type of cables, and that also linked to the amount of connectivities you may have, and they could be very complex. So, which means then you need to think about the payload in a car or in an aircraft, and how you would repair or identify any issues you have, the durability of the systems you have, and how you do the connectivities either during the construction or during a repair. This becoming complex and complex with the need of or demand of the customers. So if it's not wires, what options do you have? You could think about wireless data transmission, but you need to think about what sort of signal data you want to send, and are there any restrictions or shielding depending on the structures you have, and what sort of reliability you want and you need, specifically if you think about things like control data or actuation, and also what sort of speed limits do you need depending on what sort of data you send. When we talk about electromagnetic wave, generally you are aware of Wi-Fi, but actually that's a free space wave. But we also have, some of you may have heard about ground wave or surface wave. That's a different type of electromagnetic wave that has been around. It's nothing new. There for a very long time. It has been actually used to send data or signal through the earth. And the signal get trapped onto the earth based on the dielectric properties of earth, the sea and the air, and there are certain differences. Based on that, you can send data to a very long distance. And these systems or this type of technology has been out there for a very long time, for hundreds of years. And these are some of the people who have studied. So what I always say is, what I'm trying to say is, what I'm showing here is no black magic, but we are applying it in a little bit different way. So I mentioned to you about sending this data through Earth. If we want to send the signal through a material, then what's the requirements? You need to generate the correct waveform in order to launch a electromagnetic surface wave. Then you need the correct media so that you can send the signal through in a very long distance, depending on your requirement. Then you should be able to receive the signal and do whatever interpretation you want onto that signal. And this is just a simple diagram here where you get a signal transmit and signal receive, and you have a propagation media. And because the signal is not propagating through air, the signal strength speed is much higher, the reliability is a lot higher. So now, how does this link to composites? So nowadays, as you may have heard and you may be aware of, composites are being used more and more in aircrafts and in cars. And there was a time where composites are used in high-end cars, but now it's becoming to more consumer stage as well. And it's been used because of its high specific strength, which means you need the weight is a lot less, but you get stronger material, which means if you get a light structure, or you can increase your payload, whatever the way you want. So the idea is other than using as a structural material, can we have added functionalities in composites? So in relation to this talk, can we use a composite structure itself to send an electromagnetic wave? Well, the answer here is the answer is yes. So if I go to the principle of the technology, is that we send an electromagnetic surface wave through the composite. How do we do it? We have a signal launcher. That's the transducer you can see on the, to turn a bit, the transducer you can see on the left-hand side. And then you can see the composite itself. And then we need a dielectric layer and we need a conductive layer. Although we have a conductive layer, this doesn't carry the signal. It's there only to eliminate the signal escaping from one surface and reflect that signal back onto the opposite surface. Then the signal gets trapped between the composite and the dielectric layer. The reason being the composite itself is a dielectric layer, but the dielectric resin layer we have shown here has slightly different dielectric properties, and therefore you get a signal trapped onto an interface. So if you look it from the, this is the top view is the cross-sectional view. And if you look from a composite in a top level, so this is the dielectric surface, and you can see the signal propagation. This is in the simplest term possible. I have a little video that would give better feeling. So we launching the signal from left to right. We launch the signal, the conductor layer in this case is in the bottom, and the signal gets trapped on the dielectric layer. So what we are showing here is, because it's an electromagnetic wave, you can see it as a bit like if you drop a pebble into a lake, how the ripple get diffracted. So in this case, if you have some sort of an obstruction, the signal will find a path around. Whereas if you, for example, take a cable and the cable is damaged, you will lose the signal. In this case, as long as there's a continuous path, your signal will still propagate. And this is an obstruction. This one is an actual damage, and you still find a distance. Although the signal actually propagates, there is a change in the signal signature. So other than using it to capture the data, if you would like, if you want to make your structure much more smarter, you could actually use it for structural health monitoring, for example, and actually determine what damage there is and where is it. And that is through the change in the signal signature. But also, we have something called evanescence field coming off the surface. And by bringing something to the close proximity of the surface, the evanescence field gets slightly affected. You still get the full data, but the signal signature has changed. And therefore, you can also use this composite or the surflow material for proximity sensing. However, there are many things to be thought through. What sort of distance are we looking at? And in that case, what sort of frequency do we want to use? And in some cases, depending on the data you are trying to send, your data frequency and the proximity sensing frequency could be the same. But in certain cases, you may want to use two different frequencies. So it's entirely dependent. And also, if you want to detect a damage, the severity of the damage you are looking at, what's the smallest size and what's the largest size you were trying to capture, then you need to decide what sort of frequencies is suitable for this. Okay. So the characteristics are, I already mentioned a couple. It will reroute the signal. So even though there's a damage or an obstruction, you will still get a signal. Also, the connectivity is not complex like the cables, different cable types you have. It can be, depending on your requirement, a simple connection. And what I did mention before was you can send multiple data at the same time and actually capture it through one transducer. So although you're sending multiple variety of data, you don't necessarily need variety of different connectors. That's what makes it a lot simpler. And so far the work we had done, the data transmission rate is about 3 gigabits per second per channel, so which is about 3 times faster than Cat5e Ethernet cable, which is quite high for the industry we are in. Other than that, there are some additional benefits. I did mention about the dielectric layer and the conductive layer. So far, the work we have done, we have used a thermally sprayed aluminum layer, and actually that can be used either as a lightning strike protection or for EMI shielding, depending on the requirement. I mean, this is more applicable, of course, for aerospace, but if there are certain shielding requirement, even for the car, that can be used in that aspect. So where does TWI stand with this? Well, we developed the technology, how you can send this data, the electromagnetic surface wave, through a composite. And therefore, we do hold the UK patent, the US patent, and the EU patent in certain countries. In 2019, we won the, 2018, we won the Innovation Award with Composites UK. That's a bit of background, bit of show. In terms of technologies at TWI, how we can support this, I'm not going into the detail, but just to give a bit of background, TWI is, we are material engineers. We do material development, we do the testing, we do the joining, we do a variety of areas. And in terms of this technology, we had the capability to manufacture composites, do the dielectric measurements, because in order to design the transducers and the data transmission systems you need, we need to understand the material properties, and one of the main one is the dielectric property, and we have the capability to make those measurements. Then the transducer design, you need to do simulations first to select certain number of designs for your trials that we are capable of, and we do the design and the manufacturing, and any composite related testing can be done at TWI, including environmental testing. And right now, we are also developing, as part of a co-research program at TWI, we are developing a surf flow test bench where you might be able to bring a composite and tell, can you test this, whether we can get surf flow to work on this. We are developing the capability so that we can provide you reliable data. It's a bit similar to anechoic chamber, but you don't need that extent of complexity, and you can do the test here. In terms of application, well, it's anywhere where you want to do data transmission, where you want to do data transmission, and where you can actually, where you want to do data transmission, and you have a composite, you can use this technology. The requirement is maybe your data need to be translated into electromagnetic wave, but other than that, you can send any type of control data, or you can send any information or video data, anything you want, you can send it through the composite. And it can be used for non-destructive testing or structural health monitoring. And I mentioned to you about the proximity sensing, so you can use it for distance sensing, specifically in car, and map where everything is as shown in this structure. But that's in a car, but in reality, you can use it anywhere. So in the car, I have given few examples possibly where you want to control your side mirrors, or where you have your parking cameras. All the data can go through your structure if it's composite. Or actually, you don't, not necessarily your full structure has to be composite. As long as there's a continuous composite part in it, we can send the signal. Although I said continuous, if it has joints, we can manage joints depending on the frequency you want to use. One of the interesting part, you might see why there's an office. In this case, the table might be a surf flow composite, and it's a secure room where you, maybe automotive industry don't want to, leak any of their confidential data. So the surf flow is the table here, and the people who are joining the meeting and coming to that meeting might be coming with their laptop. The laptop is actually have the surf flow transducer, but it will get connected to the network only once the laptop is placed on that table. So that's in terms of security. Or I think Steve mentioned about the car coming in and the sensor data being extracted, and actually that room or the floor could be a surf flow floor, and the car has surf flow transducers, and as the car comes in, all the sensor data from the car could be extracted. I have a few demonstrators to explain this a bit more. So this is one of the very early demonstrators we did, which is a video transmission. So here you see there is the camera on the left-hand side. Actually, just to add to this, we are sending data so far. We are not sending power. So either you still need the power cable or you need isolated power source. So in this case, there are batteries. And I mean, there are advantage of it and disadvantage. Of course, if you can also send the power, that's the best. But in this case, actually, the power requirement to send this signal is so low. It's milliwatts. So you don't need a lot of power. The smaller, the better it is for this technology. So that's the camera. That's the screen. And again, you have a separate power source for it. And that's the surf flow composite. And you can see at the two ends, there are transducers connected. So the idea is to show, okay, if you put your fingers on, you still get the signal. The only way to, so I mentioned that you need a continuous surface to send the signal. As long as there's a continuous path, you will receive the signal. But if you disrupt the full, the width of the continuous path, then that's when you lose the signal. You can see here when you disrupt the full width, then you will lose the signal. That's the idea. The next one is to show that we can send multiple signal at the same time, and it's a model, a glass fiber model aircraft. So here you can see there are no cables, there are actuators. And there are individual power sources in there. And the fuselage doesn't have any cables. And in this case, the transmitting transducer is at the tail. And what we want to show is that you can send multiple signals at the same time. That's switching on the individual power sources. And you can do the control at the same time. It's the way I like to usually describe this as it's very similar to Wi-Fi. You can do everything you do in Wi-Fi. The difference is the signal is transmitted through the material rather than through air. The last demonstrator is a robotic for robotic applications, but it could be in car manufacturing. And again, the aim is to show that you can send a number of signals at the same time. So yeah, that's the end of the presentation. And I hope you enjoyed. I can see some questions. Let me see. I don't know whether it's for me.
Yeah, they are, Jasmin. And I was just thinking we might cover those now.
Yes.
Do you want? Right.
The first question is whether the lightning strike protection has been tested and modeled. The model part, I personally don't know. It's not my area. However, even the application of the thermal spraying is a different area. Actually, Melissa is presenting in one of the sessions today, but that has been tested. The system has been tested for lightning strike protection. Yes, I assume part of the study has been modeling. If you want further information, I can put you in touch with my colleagues who are actually doing the thermal spraying.
And then second one is, how would the signal within the composite interact with impact current non-destructive testing methods like ultrasonic? Or would it replace current ND testing methods?
That entirely depends on the requirement. There are more work to be done in this area. This is mainly the principle. It could replace, and in certain, depending on the complexity of the understanding you need, you may be able to combine it with a non-destructive testing method. For example, I might be able to, so sometimes, for example, in construction, when I say construction, in manufacturing of aircraft, with composite parts, you generally scan the full part, but Surflow might be able to tell you where the damage is. And if you want to understand the damage in details, because Surflow so far cannot tell you whether it's a delamination or whether it's a fiber fracture, for example, we could be able to tell where the damage is, and then you might be able to use a complex method, for example, something like X-ray computer tomography to understand the damage further. I hope that answered my question.
Okay, right. Well, we're now left in what I would call a little bit of a quandary, because we had hoped, to cover, LIDAR, and the presenter on behalf of Automotive obviously is in the west coast of the US, and whilst they were all confident that they would be able to do it and have agreed to do it, it seems that we are left in the position where we don't have that presentation. I mean, I think the talk that Jasmin has given over the things you can do with composites, shall we say, is quite relevant to LIDAR. I don't really want to put my colleague Rob Furlong on the spot, but I wondered if Rob would sort of care to comment. Rob's expertise is transport systems and not specifics like this. But I know Rob was involved in a project with government on connected vehicles, and whilst that's also relevant to passenger vehicles as we move into more busy roads, I wondered if Rob, you'd like to comment on some of the demands in that space that could be addressed by this.
Yeah, thank you very much. Yeah, I mean, LIDAR is a really good sensor technology. I think we've got to come back and sort of split the difference between connected autonomous vehicles and cars of the future. And what we're looking for ultimately is safety, whether that is on a connected autonomous vehicle or a standard vehicle that is out in the road at the moment. And what we're trying to achieve is 0 deaths on the road. And if we can do that with more intelligent sensors on the vehicles to make the vehicles a bit more self-aware and be able to react quicker to the environment they're in and to save lives, then that is always really positive moving forwards. So LIDAR is a sort of a typical example of that. It provides a methodology for the vehicle to look at its surroundings and to be able to try to anticipate and understand the surroundings that are happening. And that output could either go to some form of braking system or solution, all the way through to navigation type systems if you're looking at a connected autonomous vehicle. But the importance is if a vehicle can detect an object that it's in its path, and the vehicle can then deduce that if it continues at its current trajectory and current speed, it's going to hit that object, then obviously the vehicle itself can make some decisions on assisted braking or assisted steering to help the occupant. Now, at this moment in time, obviously, where we are with vehicles with a driver in the driving seat, we have adaptive radar systems already for driving along the road, where the vehicle will keep a constant distance in front or behind the vehicle in front of it, so adaptive cruise control. The vehicle is being used in an intelligent mode at that point, but the driver is still in control. It is not an autonomous vehicle in any way, shape or form. And the same thing will happen, can happen when you're driving in a pedestrian zone, etc. And what can happen when the vehicle detects the object? It can do one of two things. First of all, a bit like adaptive cruise control, it could apply the brakes to avoid the object in front. The second thing it could do, actually, there's a finite time when you press the brake pedal to the brakes actually engaging on a vehicle. Might be 100 milliseconds, 150 milliseconds, and that is effectively, it's a pressure system at the end of the day. It's a fluid system. That fluid has to be compressed at the pedal, transmitted across the whole system to the actual brakes to apply the brakes, and that takes a finite amount of time to do. Well, actually, if the vehicle has detected that particular object, it could preempt that the occupant, the human in the loop, is going to press the brake, and therefore it could prime the brake system up to reduce that 100, 150 millisecond delay. So when the human does apply the brakes, they actually instantly come on to slow the vehicle down even quicker. So, I mean, there's some really interesting applications there for LIDAR and LIDAR systems. I also see another type of system we haven't seen here, which is starting to look at the bouncing of light from around the corners, so that a vehicle can detect if an object is coming to it from an acute angle, and again, if the two are going to collide and hit, and therefore the vehicle can take other action as well. But I mean, it's all about safety in automotive, and certainly any vehicle that is driving, and how can we use sensors and technology to save lives on the road. And so there's a sort of a brief thing there for vehicles, Steve.
Thanks, Rob. I mean, I was thinking, obviously when I'm sort of thinking about this, I'm thinking about, if we consider that metamaterials are there to help focus radiation in way, shape or form, whether it's acoustics or down to IR and RF and the like, is that the sort of, if we could add value with that sort of focus, is that the sort of thing that's required in these safety aspects in general? That's all I was thinking. So whether we're talking about connected vehicles or just general safety on busy roads, is it an area that we should be looking at? Is that, I think obviously the automotive manufacturers like Toyota and BMW have, but I don't know how much has been adopted.
I mean, it is being adopted and has been adopted, but I think it should be worked on more and more moving forward as the frequencies are used differ. So, for instance, I remember a time when we were using 2.5 and 5 gig doing vehicle detection and intelligent tags on vehicle testing many, many years ago. And actually 5 gig loves corners and 2.5 gig loves a corner. And what we found is that if you had an articulated lorry in front of the vehicle, actually the RF signal would travel down the edge and then radiate at the back of the articulated lorry, and therefore increase the communication zone of detection system you're doing, and actually falsely placing where the vehicle is, where you think the vehicle's in the communication zone, but you're not. You're actually 15 or 20 meters away from it because of this effect you're seeing. So absolutely, the RF capabilities of the materials being used need to be understood to understand the environment they're being used and utilized in. Thanks, Rob.
I've got a question for you, but I know Jasmin's got another question that's come from the floor. What's the cutoff frequency, upper or lower, for where surface waves stop being supported or reasonably accurate?
We don't necessarily have a upper or lower limit. The work we have done so far is, the lower limit we had tested so far is 2 to 6 gigahertz, and the upper limit we had tested is 50 to 60 gigahertz. Doesn't mean that those are the only frequency that it supports. The reason why we had done the work in 2 to 6 gigahertz range is because we used off-the-shelf Wi-Fi electronics, modified it for surf-flow technology, because those are the widely available electronics for us. But I don't see why we cannot go lower. How lower? We haven't done the full test. And it depends on the requirements and your materials. So far, what we are trying to do is we are not asking necessarily people to change their structure. If they already have a composite structure, our aim is to try to adapt our system to match their existing structures, because I know how difficult it is to get the system certified or a material certified. However, if you are designing a new structure, then yes, we can think more into the details or proposing new materials and change the structure to optimize the use of surf flow. So the highest frequency we have used is around 50 to 60 gigahertz, mainly due to defense applications. Again, I don't see why you can't go higher, but it gets more expensive in terms of electronics. And then the consideration for things like joints would be higher, because all these are dependent on your wavelength. So if you are using 2 to 6 gigahertz, the joints of a composite is not a big issue, but because the wavelength is larger. But if you're going for higher frequencies, your wavelength becomes smaller. Therefore, things like joint has to be very carefully designed. These are the things you need to take into account.
Thanks, Jasmin. Rob, there's a question for you, but I don't necessarily think it relates to metamaterials. I don't know whether you can see it in the chat about reports that braking systems in certain vehicles have failed due to weather and icing of sensors. How can industry address that and make sure that high-tech systems aren't defeated by the weather? I suppose that's a generality on, if the more tech you put in, is there more chance it'll fail because of the weather?
The thing, yeah, absolutely. This is a sort of a challenge. Is obviously sensors and data is only as good as the sensor is in the environment it's working in and the location it's located on the actual vehicle itself. And you know, you have to make sure that the sensor that you are using and putting in actually can cope for all conditions that the vehicle or the environment that that particular sensor needs to be in can cope for it. Otherwise, you haven't got the reliability. And there's no point in putting sensors on a vehicle that works in the UK to find actually you put it to the outer Siberia or somewhere like that, where it goes down to -30, -40 or 50, and the sensor fails and doesn't work. So yeah, it's about just making sure from the automotive industry that they use the right sensors, but from a material point of view, it's making sure that those sensors are reactive and can still work within those defined weather parameters. It also comes down to where the sensors are located on the vehicle as well at the end of the day, and are the sensors protected as well. So there's other factors that can be brought in, but the most important thing is understanding at a fundamental level the environmental parameters that sensor will work in, and understand where the failure points are on that sensor, and making sure it's used well within the failure points of the system. It's about testing and using the right sensors at the end of the day.
Did you ever ask did you ever address, when you were looking at the stuff, the connected vehicles and that, and autonomous vehicles, was it ever considered, how much energy would be required to power such a vehicle or such a system compared to, a standard car? Because at the moment, we know that electric powered cars, unless you're spending huge amounts of money on a Tesla, which seem to be quite reliable. In fact, quite a few others can run for that sort of 300 miles. But, if you're piling on more systems, does that mean that, we're going to be challenging batteries even more or whatever? Yeah, well, it'll be batteries, won't it? Because obviously they're the things that are powering cars and probably will continue in the future. I mean, is it a question that was addressed or not? Or is that something we should be thinking about?
It definitely needs to be thinking about, and yes, it was addressed. To answer it in a very short way, to go into a little bit deeper, when I was first looking at connected autonomous vehicles, it was calculated you need at least 2 to 5 kilowatts of power just to run the processors to do an autonomous vehicle. This is obviously right at its initial point. So yes, the power requirements were thought of and required. And that power is not only the electrical power coming in, but it's the heat dissipation from the electron components as well. And what we were then looking at, and what the community was looking for, is the fusion of sensors. So instead of having a separate radar system, a separate LIDAR system, a separate camera system, actually could that be one sensor that provides either multiple outputs or the same output that then can be used? And obviously the modern processors and computing power have come on a leap and bounds, but also so is industrial mathematics, where you actually make the algorithms that you're doing quicker to implement in code, which means you don't need so much power. But we are at that point where, yes, every single sensor that you put on that requires power is going to draw power out of your electric vehicle. And it's a very balancing dilemma at the end of the day that the automotive sector has, based on safety, reliability, and how long you can drive your vehicle for, as far as mileage when you go to electric vehicles. But yes, it's been addressed and looked at. And in the materials world, sensors that can take less power and use less power and demand less power are obviously going to be more attractive moving forwards.
Yeah, I think it's a huge area, isn't it? That, you know, we are challenging ourselves more and more with the requirements of, you know, for energy, and then of course things like energy harvesting, for instance, become much more important, because, you know, you can only have so much in a battery, but if you can obviously, you know, generate stuff from the, you know, from around you in the environment, that's a big positive.
Well, of course it is. And I mean, just to sort of go through that, yeah, energy harvesting is big, but what we've got to look at here is that the energy requirements of a vehicle are actually pretty high and huge. Now, obviously, electric vehicles do energy harvesting by actually regenerative braking, which is where actually you don't necessarily use traditional brake pads. You use the electric motor as a brake to regenerate electricity to charge up the batteries. But it's about sort of, and I think where the materials can come in, and the metamaterials is really how can we store electricity or power in a more efficient way, an efficient manner, and then how do we have sensors that use less power in a more efficient manner to get a whole system. And when you look at it, you've got to look at the car as a system at the end of the day.
Yeah, I think storage is a big issue, isn't it? It really is a big issue. And indeed transmission, because, you know, you load stuff in transmission as well. So yeah, it's a bit interesting area. I think we've got another question for you, Jasmin. I don't know whether have you read the question in the chat box? What is the shielding effectiveness? Yeah. Do you want me to?
Please do, yeah.
Yeah, the question is, what is the shielding effectiveness and losses of your metamaterial structure versus a standard coax cable for given frequency ranges? 1 to 10 gigahertz. It is what's quoted in the brackets.
Yeah. Well, we haven't done a full comparison, again, a standard cable. But if you take, because of the metallic coating you have, if you take a continuous structure, I would say they are equivalent. However, similar to the joint, when you design a joint, or if you have attachments to the structure and you have, for example, holes or curvatures, then need to look at it a bit more into details. Actually, that's one of the part we are currently working on as part of internal study, how the limits and how the different structures would affect any potential losses, more than actually losing the signal strength. So far, we haven't had that problem, but in terms of security, what would be the influence is something we are testing at the moment.
Thanks, Jasmin. I think there's another one here as well, which is you've covered the issue of joints and composites and the effective wavelength. What if you need to transfer from one composite to another because the vehicle's not made of the same material? So
that depends on the material.
Yeah,
that depends on the material. If for example, if you take the frequency I mentioned before, 2 to 6 gigahertz, the complexity is a bit less. As long as there is compatible dielectric properties, then we are able to send from one composite to another composite. But of course, if your structure is a hybrid where one part is composite and then you need to send signal to the metal, then it's a different story. It's not the same, but we can do certain things to accommodate, but it's not the same. But if you go for very high frequencies, then your composite composition in terms of its what do you call the unit cells, that means the view patterns in the composite may have an influence. Then need to look into more detail. But for 2 to 6 gigahertz, it's a bit more straightforward.
Thanks, Jasmin. Right, just to put Daisy on the spot, because she's hiding behind her picture at the moment, I wanted to ask her what she's heard that we've been talking about in the automotive area. What is relevant to, or what might be relevant to the rail area? And I'm thinking particularly of acoustics, because we know that things like high-speed trains create a lot of noise, and we know that we need to address that. Is there a way we can, I guess, take account of some of the things that we're developing in the space for automotive that could be relevant to the rail side? And I mean, that includes everything from harvesting energy to focusing Wi-Fi signals and the like. And I just wondered if the rail sector was looking at those sort of things too.
Yeah, definitely. And for the audience, again, my area is very much rail rather than metamaterials, but there's a huge amount of crossover. I think, as you say, there's the noise element of this, and that is obviously firstly kind of the trains themselves. So a really big part actually for us is the impact of night services, but freight trains specifically as part of that overnight. So one of the biggest kind of elements within that obviously is excessive noise being irritating, but that kind of impact on human health as well. So the noise impact there, and I know we had conversations in our acoustics and thermal session this morning around that as well, the impact on human health as Gianluca outlined for us. But we also know, one really interesting fact I actually found out reading articles around this topic, the British Medical Journal published a piece around the noise of passing trains at night actually obviously affects your sleep, but that then can induce an acceleration in your heart rate, and that can be linked to cardiovascular disease. So there's all sorts of kind of the human factors around that. So firstly, I think, yes, that kind of noise mitigation, and we talked quite a lot around barriers and panels as well this morning. So there's a huge piece there as well. But then also kind of thinking, I know there's lots of work going on in the space in, you've mentioned to me, Stephen, a few times, the curtains for the NHS in, reducing sound and that kind of thing. So also materials for train interiors, I think, is a really interesting application that's definitely not being picked up as much as it could be in the sector. So actually making rail travel a quieter, calmer experience, especially as we're looking, obviously after COVID, to attract our passengers back, anything we can do to boost the passenger experience. So I think that's a really rich area that could be explored, but certainly there is work going on in the noise space, but in rail applications, it takes time to get anything into rail. So it's definitely something there's a lot of opportunity in.
I think that's true, but actually a lot of things, and one of the biggest challenges for metamaterials is not only the fact that people sort of aren't really sure what they are necessarily, or what the real definition is as far as they're concerned, whether it's relevant to their sector, but more importantly, how do you fit them into the manufacturing process, and how do you test them, and how do you have standards? And I think rail is no different to the automotive or the aerospace sectors, which all have requirements for new materials, and you sometimes think, are you going to get them into that space? I think that's maybe why we see a lot of sort of small SME type, spin out companies trying to pick up technologies and move them into the space, because it's something that perhaps somebody who's got a passion for can do because of the hoops they have to jump through, whereas a large organization maybe would be put off somewhat. I mean, it's an interesting thing, isn't it?
Yeah, it definitely is. And your point on standards is really well taken. So, I mean, if we think about Network Rail, obviously in infrastructure terms in the UK, 20,000 plus miles of track, 30,000 plus bridges. I mean, we're talking about, and other obviously railway structures and buildings, we're talking about a huge amount of work. And that's before we even talk about the construction side. So thinking about High Speed 2 is the really obvious one, but then all the work that's ongoing across the country, the Transpennine route upgrades as well. So there's a huge amount in the construction space directly that can kind of come into rail as well. So that mitigation on the human impact, that mitigation in the construction sense as well. So again, this morning, Pete mentioned in the session about the impact in construction terms of large machinery and the impact that can have on their actual users in terms of productivity. Even mentioned fertility impact, which I had no idea. So there's a huge opportunity again for bringing that into rail, but then also the environmental impact. So again, if we think about high speed 2, one of the biggest, obviously, public areas of focus around high speed 2 is the environmental impact. And whatever major construction projects like high speed 2 can do to mitigate that impact is going to be really important. So if we think about noise and vibration, not only from construction, but also from rail, has impact on things like the health and viability of bird populations. So that can have an enormous impact, obviously, across the natural world. So I think, again, thinking about this in, yes, rail terms and passenger terms, but also the impact that that has on the entire landscape around a network. So again, quite similar to rail. To road, rather. There's a lot of crossover.
Yeah, because I know that, you know, national highways have similar issues, especially around things like bridges and the nature of the noise. I mean, it's quite a challenge. Well, unfortunately, we haven't got our speaker on LIDAR, and we have covered it. I don't know whether you know, either you, Rob, or Daisy want to say anything else, but at the moment, I'm thinking that we haven't got any more questions coming from the floor. And I don't want to keep people hanging on if there's other sessions they'd like to join. I feel we've perhaps explored ours as much as we can with the resource we have. Yeah, Rob, go on.
Yeah, well, one more point, and obviously Daisy sort of mentioned as well, was the environmental impact of transport, and certainly when you look at the car and the motor vehicle at this moment in time, yes, we're changing from diesel to being more environmentally friendly, with petrol going down to hybrid vehicles, going down to electric vehicles, and we have that pathway. But actually, it's not just the fossil fuel that causes pollutants in the atmosphere. As Daisy's mentioned, yes, there is the noise of the car itself. Now, some will say actually the noise of a car is actually quite good, because obviously we've got to have the awareness of the human population when we're crossing roads to look for electric vehicles, not just say we can hear them. And obviously that's a major thing. But there's two other areas of pollutants on the vehicles, which is nothing to do with the fuel we use. The first one is the tires. And my question is there a metamaterial that can be developed or looked at? And Dunlop and other vehicle tire manufacturers are not going to like me for this, but actually major particulate matter pollutants that are created come from the rubber tires that are on the road surface. And you can imagine, as you're a pedestrian walking, you're only about 4 foot away from where those tires are, and they're generating particulate matter that's coming up in the atmosphere. So that's the first one. The second one at the moment is your brake pads in your vehicles. And yes, I know that there are composite brake pads as well, but they still wear down every time they're used, and they're still putting a huge amount of particulate matter into the atmosphere, which are causing problems as well. Now, we did talk about regenerative braking, and that's moving across to there, but that's not here at the moment, you know. So there are other things that are on the vehicle that are causing impact into the environment that we need to look at and investigate further.
Yeah, I think, yes, that's interesting. I mean, all I know that's going on in this tire space is that there has been a lot of work on the use of graphene to extend and improve tire performance. And I think that is, you know, generally to improve tire life, which might help to, you know, reduce particulates, but it's not really metamaterial. It's just something that, you know, that is known. Yeah, it's a big challenge, isn't it? It's a big challenge.
It is a big challenge.
A lot of things to think about.
Yeah, absolutely.
Yeah. Well, I'd like to thank everybody for presenting, especially Daisy and Rob for actually stepping up and sitting on camera and saying stuff, because that wasn't originally the plan. Thanks again to Jasmin for her presentation and for making people think about, you know, what we could do with composites. And I'd just like to thank all of you who've tuned in, and hope that you enjoyed it, and that we didn't disappoint you too much. We will, of course, be sharing some of the findings from this, and I'm hoping that whatever happens, I might get some input from our American friend who wasn't here today, and perhaps share that after the event, subject to what we're allowed to share. I'm not planning to share any of the recordings of the sessions and that, but we will write a report which will have some of the findings in it, so maybe we can add something into that. I'd just like to thank you all for coming, and if you'd like to try and attempt to get into one of the other sessions when you finish watching this one, you've got another 25 minutes, I think, of some of the other sessions that are running, which I can tell you now at this point in time are, what are we talking? We're talking about the built environment and construction and creative industries, which is all about the role of design and creative industries in new product development. So thanks again.